Hello and welcome. In this edition of Astronaut Survival Training 101, we are going to conduct an experiment to once again determine the acceleration due to gravity, but this time we're going to use a pendulum to do it. The lab is based on this equation that says that the time squared, the time that it takes a pendulum to oscillate squared is equal to 4 pi squared over the gravity field strength times the length of the string. All right. So by varying this quantity and measuring the time and squaring it, we can plot t squared against L and the slope of our best fit line. We can set equal to 4 pi squared over g, solve for g, and know the gravity field strength that's accelerating this mass. You can see that I've already collected my first data point. This is 0.548 meters long. I've got my stopwatch ready. You can get yours ready at home. And it doesn't matter which 10 oscillations you time. So I could set this thing moving right now and say, oh no, you got to start over. I didn't start timing it. It doesn't matter. Just time any 10 oscillations. So I'm going to start timing mine right when it gets back to here. 1, 2, 3. And in case you've timed a separate 10 oscillations, a different 10 than I've timed, I let it go a bit longer than the 10 that I counted. But for my 10 oscillations, I timed it to be 14.98 seconds. Which is, again, it's convenient to just time 10 oscillations because then we know the time of one oscillation is just that value divided by 10. So your data table might look like this now, where you've got, I mean, if you're timing yourself, then whatever you got for the 10 oscillations, but this is what I got, and then you see I just divide it by 10, it's just moving the decimal point up. Now 1.498 squared, I think everybody knows is 2.24. So that's one that you're going to calculate, right? So there's my first data point. All right, now I'm going to go ahead and vary the length of the string. I'm going to do this by just sort of wrapping the top of this thing around here a few times. And the new length is 47.1 centimeters. So 0.471 meters. That's ready to go here. Release. And then go ahead and just time any 10 oscillations you want to. All right, hopefully you got a good time for any 10 oscillations you wanted there. This is what I came up with, 14.19, so it's a little bit less time. And then dividing that by 10, 1.419 seconds squared is 2.01. So I'm going to plot, these on my y-axis against these on my x-axis. I suppose I could be done with the lab right now. Just plot these 2 points, find the slope between them, everything will be done. But that's not a strong procedure. It's much better if we can continue to vary this and plot a whole set of data and then look for the trend in that data, draw a best fit line. So we're going to keep on going. I'm going to go ahead and decrease the length of the pendulum string a bit more. A bit more than that even. All right, so now I've got a shorter length of string. Move this view slightly this. And now I've got a length of string equal to 34.8 centimeters. So 0.348 meters. We'll set that in motion here. Time any 10 oscillations you want to. All right, you might have noticed that in addition to like the motion this way and this way, it's starting to sort of sweep out like a conical pendulum. And that might be affecting the results a little bit too, especially like when it crashes into the ring stand there. All right, for that data point, I got this. So I was getting 0.348 meters of length, took 12.25 seconds to oscillate 10 times, which means on average it took 1.225 seconds to oscillate once. And that quantity squared is 1.50. Vary the independent variable yet again. Shorter string. The last one?
Yeah.
0.34, the one I'm doing right now?
Yeah.
I haven't measured it yet. I would say, you want my best guess, 24.8. Let's try that, 24.8. Don't write that down. Okay. Oh man, how sweet would that have been? It's 24 even, you guys. It's 24 even. So 24 centimeters is 0.240. I'm still a little bit impressed with that. So 24 centimeters exactly, right here. All right, and we'll go ahead and set it in motion. Time to oscillations anytime you want. Note that we've established a trend here where as the lengths are decreasing, the time squareds are also decreasing. And so we don't want any violation of that trend we want to be suspicious of and sort of recollect any data we might need to. So far so good here. Got 4 data points. And let's go for at least 1 or 2 more here. So if we go wrap this around here a couple more times. Smaller still. The length of this string, the center of mass of the pendulum is now 15.6. So that's 0.156 meters. How long will it take something that long to oscillate here on Earth? Because remember, the length of this string and the gravity field that we're in, those are the only 2 things that affect the motion of this. Here's what my data table looks like now. I've got, for that one, it was 0.156. It took 8.39 seconds, so less than a second now per oscillation, 0.839. And if you square that, you get 0.7. 1, 2, 3, 4, 5 data points so far. I think the data really suffers here when it's this small. Okay, it's just a tiny pendulum now. This will be our last data point before we go to plot and try to reach some conclusions. And so now it's only 7.5 centimeters, and so 0.075 meters. Yeah, we'll do a better job. All right, so let's go ahead and plot this data. All right, there's my final data point at 7.5 centimeters, which is 0.075 meters. It took 5.92 seconds to oscillate 10 times, so 0.592 seconds per oscillation for single oscillation, and that quantity squared is 0.35. Note when you square things that are less than 1, right, they get smaller. All right, so that's the data there. You might have different times if you were sort of timing for yourself, nothing wrong with that. You might have different lengths if you were sort of using your own apparatus to conduct this lab investigation. At this point, I'm going to go back over to the document camera. Go ahead and plot the data, so stand by momentarily for that. All right, we're back here. So here's once again the data table for everybody that was trying to frantically copy it down and maybe didn't have a chance to get all the data. If you need a piece of graph paper, I got a whole stack of it back here if you want to plot this data now. If you all want a graph paper journal, take one. That's for you guys. And if I got a whole journal of graph paper back there, you're like, hey, I want to do all my labs in a journal like this. It's up to you. But you can just grab a single piece of graph paper if you want. Grab yourself a clear plastic ruler too, right? So I mentioned the last time I was did have a clear plastic ruler. Several of them. Didn't have a clear ruler when you're going to draw lines at this, you can kind of judge, the bounds of your data points, kind of see them through the ruler. All right. In order to get more stellar conclusions here, we'll go ahead and use this cool Star Wars pencil. So use that. All right, a lot of this will just be sort of a review of stuff I've already talked about. So
Same rules for graphing that we covered last week, same conclusion we're reaching, but just a separate way of doing it. So if we're really interested in a conclusion, we might conduct both of these investigations, dropping things, timing them, dropping pendula, timing them, and then comparing our results. Separate labs to get to the same conclusion. So I'm trying to give myself most of the graph paper to actually plot my data. I know that I want to plot the length in meters on the x-axis, and so I'm going to label that clearly. I know I want to plot the time squared, measured in seconds squared, on the y-axis, and so I'm going to label that clearly. Let's start with the x values, and so the length. The lengths vary from 0.075 to 0.548. So we want this to be like 0.55, somewhere around here, and this to be like, I would say, a true zero. Although we could break the graph and start, like our first square. If you break your graph, it's saying there's no true zero, you use this symbol to denote that you've broken the graph. And so I could say if my first point is 0.075, that's kind of a nice round number itself. So maybe I'd make this square right here my 0.075. So that's less than 1 centimeter. I'm going all the way up to, I'm sorry, that's 7.5 centimeters, and I'm going all the way up to 50. All right, so if this is 7 and I want 55 to be about here, 48 centimeters, and so I want 7. So I want to be about 30 or so by here. So maybe I go up by 2.5 centimeters each time, so this would be 5 centimeters. So all right, I'm going to change this right away. Always choose like what's going to make life easier. Don't make it hard. It's hard enough without us working against ourselves here. So rather than calling that 7.5, I'm just going to call it 7. So 7.5 will be a little bit to the right of it. Okay. So if that's 7, I just go like this. I don't think there's enough to go 7. So I have to probably go up by maybe 2 centimeters. So this is 7. Oh, it's also not good to start on an odd number. But that's okay. So this is 7, 9, 11, 13. Yeah, I'm just going to go up by 2 centimeters every square. So this is, and if I did 0, 2.5, 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55. That's more than half. That's not too bad, but then I have some dead space there. So we'll just stick with this. Okay, so I'm going to start this line right here. The first line, it's not a true zero. In other words, from this to this is really 7 centimeters, but I'm just saying there's not a true zero here. I've broken my graph. So this is 7. This is going to be 9. This is 10, 11. So 0.11. This is 13. This is 15, 16, 17, 18, 19. This would be 21 centimeters, 23. This would be 25 centimeters or 0.25 meters, right? I've scaled it in meters. So I'm just going up by 2, but I'm starting at 7 centimeters, so 0.07 and so on. So this is 25, 27. This would be 0.29, 0.31, 33, 0.35, 37, 39, 41, 0.43, This would be 0.45, 47, 0.49. This would be 0.51. This would be 0.53, and this would be 0.55. And you can see that that did a pretty good job of getting all of my data included, because my highest value is 0.548, so it'd be a little bit less than this, and it's more than half the page. So this is, you know, even though it's kind of like got some odd values in there, it's going up by a nice even amount, 0.02, 2 centimeters a square. For the t-squared part of it, we're going from 0, here I think I will use a true 0, all the way up to 2.24. So like if this is 0 and 2.25 is about here, then this is like around 1.25, so 1. So it's like, maybe I could do every 10 squares. So I could go 1, so it'd be 0.1, 0.1, 0.2, 0.3, 0.4, 0.5, 6, 7, 8, 9, 1. And that might even be not enough, because if I just doubled that, it'd be at 2 right here, and that's not halfway. So I can go even better than that. Instead of every square is 0.1, every square is half of that, 0.05. So which means it's going to be every 2 squares is 0.1. So I'm going to go 1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1, 0.11, no, that's 1. I think that might work. So if every 2 squares is 0.1, so 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1. 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9, 2, 2.1, 2.2, 2.3. So that works, but only just barely. So I'm actually gonna adjust my graph paper. I'm gonna go all the way sort of to the top here. I need all that room. I still want to make sure that this is labeled, so time squared and second squared. And so if I stick with this scale, I'm doing every 2 squares is 0.1. My graph paper is big enough that I can do that. So if this is 0.1, that's 0.2. This would be 0.25 right here. 0.3, 0.4. This square right here would be 0.5. 0.6, 0.7. So this would be 0.75, 0.8, 0.9, 1. 1.1, 1.2, 1.25, 1.3, 1.4, 1.5 up here, 1.6, 1.7, 1.75, 1.8, 1.9, 2, 2.1, 2.25. Okay, so 2.25, you can see it's, maybe you can't see, at the very top of my plot. Okay, so I chose a really tiny scale to spread my data out over, you know, a good vast majority of the page there. So there's, I'm ready to start plotting some data, reaching some conclusions. The first one I'm going to plot is go over to, and I'm plotting it in the order we collected it. So my first data point is going to be way up here, and then I'm going to sort of work my way down this way, right? Because I started with a long string and I made it shorter. So I'm just, the data will still be a positive correlation. It doesn't matter what order you plot it, it'll fall into place, but I'm going to plot it sort of like this. So the first one is 0.548. And so I want to sort of remind myself that each one of these squares is 0.02. So 0.548. This is 0.53 and that's 0.55, then 0.54 would be right in between. 0.548 is almost 0.55, so it's nearly like touching this line. And it goes up to 2.24 on the y-axis, and so I go all the way up. .2, 2.15. So I'm sort of reminding myself what the scale was over here, right? So I've got 2.25, but I want 2.24. So that's 2.2, 2.24 is just touching sort of that line. So we go here, up on this one. So our first data point like that. Okay, so again, 2.24, 0.548, that's our first. All right, 0.471. So if I look at my x-axis, I'm going to 0.471 now. So I've got 0.45, 0.47, 0.49. So 0.471 is just touching sort of this line right here. This is 0.47. So we're just touching the sort of outside of that. Up to 2.01. So it's basically on the line corresponding to 2, which is this line right there. So there's my first two data points, 2.01, 0.471. The next one was 0.348. So 0.33, 0.35. So it's in between those two, 0.3, almost 0.35, right? And then go up to 1.5 even. That's kind of nice. So this one goes all the way up to 1.5 here. So far my data looks like this. I can see that I got a nice little trend there. Keep a good thing going, 0.24 on the x-axis. So there's 0.23, 0.24 between those two, 0.156 now. So this goes 0.1. Sorry, 0.24 here, 1.06, right? 0.24, this goes up to 1.0. This would be 1.05, 1.1, 1.15, 1.2. So if it's 1.06, then it's going to be just above this line right here. So if this is 1, that's 1.05, 1.06 would be right there. 0.156, that's 0.15. This would be 0.17, so nearly touching that. Go up to 0.7, so 0.1, 0.5, 0.6, 0.7. There. And then 0.075, 0.35. So 0.25, 0.3, 0.35. All right. So you can see the data. One's a nice trend line, what we expected. And I have to sort of judge where the best fit is now. I can almost draw a line in exactly through those data points, which is a good thing. It means that the uncertainties are kind of low. So I'm going to choose this line right here. And so I kind of have like one point, out here. That's a little bit below it. Every other point is basically on the best fit line. So if I had to, I could use those, data points to calculate, but it's better to find this, and let's use that one. Looks really good. So try to find 2 points that you can read off what their coordinates are from your well-scaled axes. This point has coordinates of 0.29, 1.25. This point here has coordinates 0.41, 1.75. So I sort of write out my XY coordinates. As a quick review, let's remind ourselves that we base this data collection on the theory that the time of oscillation for a pendulum is equal to 2 pi times the square root of the length of the string divided by the gravity field. To avoid working underneath the radical, we just squared everything. And we have an equation of a line, y equals mx. Because we plotted the length on the x-axis and time squared on the y-axis, we could set the slope of our best fit line equal to this term, 4 pi squared over g. Let's figure out what that slope is right now. The difference in the y values, 1.75 minus 1.25, That's the rise, right? I'm rising from 1.25 to 1.75. So the difference between those is the rise. The run is the difference in the x coordinates, 0.41 minus 0.29. So that gives me the slope. All right, so I think in the numerator up there, we're getting a half, and in the denominator, we're getting 0.12. So the slope is going to be 0.5 divided by 0.12. And I like to just kind of show all of that working there. So again, we've got the rise over the run. The difference in these is 0.5. The run 0.12. So 0.5 divided by 0.12 gives me a slope of 4.16 repeating. And now I have to set that equal to 4 pi squared over g. That's what the slope should be equal to according to this theory. And it allows us to solve then for g. That's the conclusion we want to reach. So 4.16 equals 4 pi squared over g. Multiply both sides by g. Divide both sides by the slope. And I get g equals. Think about how the units of this slope are seconds squared per meter because I rise in seconds squared and I run in meters. So the units of the slope are the opposite of what g is because g is down here in the denominator, right? So like the units of this are seconds squared per meter. The units of our answer are going to be meters per second square, like we know acceleration should be, right? The acceleration due to gravity. So if this was exactly 4, the 4s would cancel, and I'd calculate g to be pi squared, which we know this should be 9.8, and pi is 3.14, so 3.14 squared is almost right. You know, like if you're getting close to 4, you did a pretty good job. But let's see what exactly we get with these conclusions. So 4 times pi squared divided by 4.16 gives a final answer of 9.5 meters per second squared, 9.49 in my calculator, which is really good, right? 9.8 is the known value. And so that's a fine conclusion to be reporting for the acceleration due to gravity here on this planet. This has been another edition of Astronaut Survival Training 101. Take your shoelaces off, start sending that pendulum in motion, time it, plot the data as we've just done, and now you know what the acceleration due to gravity is on your planet.